Hello. Today I'm going to be demoing PA4 for Dr. Tanzir's 313 class, and this PA is based on like multi-threading and um, so we're still doing the file transfers from PA1, but we're also working on thread concurrency and the problem of producer versus consumer threads. And in this case, we actually have three threads. We have the producer thread is the patient thread, then we have worker thread, and histogram threads, and then we also um, so we also have file threads for our file transfer. And so first, let's focus on our data requests. So I'm going to go through and just show different timings for each request, starting off with 15,000 data points for each patient, 15 patients, 5 histogram threads, buffer size 1024, and 50 worker threads. So this is like the low end of the spectrum in terms of speed and timing. So we should get a really slow here. The fact that we're only using 5 histogram threads doesn't really mean much in this case because we only have 50 worker threads. So the bottleneck here is in the worker threads, and I can prove that by increasing the number of histograms. So let's say I increase the number of histograms to 20 histogram threads. I mean, it's still going to take the same amount of time, around 12 seconds. Uh, exactly. So that just proves that the bottleneck here is not the histogram thread, but the worker thread. So if we go back to 5 histogram threads and try 100 worker thread, we basically get down to like 7 seconds. And then this should just be magnified. If we do 250, say probably around 3 seconds. So we have 4 seconds, and then 500, which is like our limit for worker threads, unless we extend the limit by using like U limit. This just changes the 1024 number of processes. And yeah, at this point, it's really the same. So now if we increase our buffer capacity or our histogram thread count, let's start at 250, and then let's do 50, or let's do 20. Yeah, 20. That's weird. My CPU fan's ramping up. I've literally never heard that before. So yeah, here we're at slightly down. So I'm guessing if I try 50, maybe we get a better result. What is up with this? 60 Celsius. Hopefully my computer doesn't die. This will not be fun. There's gotta be something up. There's no typo. Open. Okay, so I guess at this point we're just gonna call it at 4 seconds. So yeah, we hit that around 250, honestly, maybe 300 worker threads. So maybe there is some coarse grain locking that I'm doing, but if we go to bounded buffer and we look at this, I mean, I'm locking before, after I make this, define this vector charge to hold the data, and then do unique lock mutex, then for slot available weight. So really all I'm doing is slot available weight, pushing into the queue data, and then incrementing the occupancy by the length of that push, which is yeah, given, and then we unlock. So this is really all that's happening in the push, and then the pop, same thing basically. Well, in this case, yeah, mutex. So now data available because we're popping around the consumer side. And then, oh yeah, so we make the vector, we define the vector inside this. So this might be causing some problems. So I'll probably try, when I write my report, I'll probably try and make this outside just to see that might give me some increased performance. Anyways, let's continue the demo. All right, go for 15,000. Oh yeah, and then also our bins, 10 bins from -2 to 2. So each of these are like 0.4, and it correctly puts in 15,000 for each patient. So we have 15 patients, and that looks pretty standard distribution on each. This guy doesn't look too healthy, but the rest of them look pretty healthy. Gross. Oh yeah. So I'm not using any. Well, I have included thread, but if I just take this out, this literally won't make a difference because in this case we're not using any of that POSIX library. We're not using semaphores, pthread. Yeah, only standard mutex and conditional variables. So we're good on that. Sorry for the one piece in the back. In addition, make sure that they're using capacity, which is limited by number of bytes instead of, oh yeah, number of items. So, yep, capacity is the number of bytes. So when we pass in the bounded buffer, let's say in when we make our threads. So yeah, request buffer, response buffer here. When we pass these are all in terms of the bytes, not the number of items. So that's how this works. We do have our histogram thread. So yeah, I wouldn't say it's coarse grain, but there is some work to be done. Let's go ahead and do some file transfers now. USB 10 worker thread, 0.35 second. Okay, passed. And now, so I already truncated the file, my directory. Oh, here it is. And so we can just go ahead and copy that. $10,000 dot data. Let's try it with 100. So half a second, 50, quarter of a second, 10, fifth of a second. Okay. And our files, so they are transferring. I should probably, shoot, I forgot how to compare them, but in any case, I can just open it. All right. And then that, so cleanups. Go through that. Always got to remember this cleanup. So first of all, here when we send a quick message, delete the channel, worker channel. When we break from this while loop. That's just for the each worker thread. And here we delete the main channel. So yeah, we clean up and to make sure in the make file, I included the sanitize address and frame pointer to make sure that when we're filing and outputting, it's cleaning up correctly. So that looks good. Yeah, we quit to every single channel, including the main channel. And so all worker channels, main channel. And yeah, so runtimes, what I can deduce right now is the worker threads, when you vary those, it's big performance gains. And buffer capacity is default 1024 bytes, but if you go lower, it's going to be slower. If you go if you increase the U limit, it'll go faster, but marginal gains, marginal gains. Main thing I want to test right now is actually just to change this mutex and declare that vector outside. And I think this can be done. This is possible. And let's just try it real quick. Make clean, make, and we'll run those same data transfers. Okay, 5 histogram threads, 50 worker threads. Ah, yeah. Heap buffer overflow. Okay, well, I guess I put that there for a reason. So in that case, I guess since we're popping, it's different to when we push because we're checking it's still there, so we have to define it inside the after the mutex lock. Yeah. Okay, I'll go ahead and make these graphs and make sure I include everything. Well, thank you for watching. I appreciate you guys. I'll see you guys for the next PA. Thank you.